Hi, this is Robert Bolaños. Welcome to part 9 of the analysis and design of a forward converter. I'm still be talking a little bit of synchronous rectification. I mentioned or introduced the concept of synchronous rectification and that it's used for. Uh, Basically, if you're going to do low voltage, high current, and you use a diode, I showed in the last that the power that I was using in the model, I believe it was a 1N6913 diode. It's a beefy diode. It's 25 amps, and we calculated that we have a power loss of 5.2 watts. So that gave us an efficiency of 86%. So that's where you would use synchronous rectification. Instead of using diodes to do your rectification, you're going to use MOSFETs. I mentioned the difficulties or challenges in using synchronous rectification. You have to get the timing correct, and you need a dead band. That was critical. The dead band is when both the on, let me see if I can show here. Dead band is when the forward MOSFET and the catch MOSFET are off, both off. Okay, because if you have this MOSFET on and this MOSFET on, if you'll notice, this is the secondary, and if both are on, you have circulating current here. You shorted your output. And if you shorted your output, then that current is going to be reflected to your primary, and you're going to have huge current in your primary. And so that's what you want to avoid. Now this circulating current, when you have that, we sometimes call it cross conduction. So that's another word that you want to be aware of. Okay, so we went ahead and calculated the power losses in the diode. Okay, so let's calculate the power losses of the synchronous MOSFETs, and I'm going to do a little bit of hand waving. So I'm just going to say, in the last example, in the SPICE, we have an average or an I out of 10 amps. Okay, so that's going to be 10 amps squared, and then we need the RDS on. So here is the data sheet, and the data sheet says that it's going to be 3.5 milliohms. 3.5 milliohms. Okay, so 10 squared should be 100 times 0.0035, so half a watt. 0.5 watts. So that's a huge attenuation, almost of order of magnitude. Okay, big drop as far as the conduction. Okay, but at the end, and let me put this here, there is no free lunch. Okay, this is kind of like an American saying. I don't know if it translates to other cultures, but when I say no free lunch, means that you save somewhere, and here we're saving the power in the MOSFET, especially the forward and the catch. We're saving a huge amount of currents, but we end up wasting power somewhere else. and hopefully I can explain that. Okay, so let's take a look at this MOSFET that I'm using in the model. Okay, this is not your typical MOSFET. Okay, this is called a synchronous rectifier. This is different from most MOSFETs in that the MOSFETs internally have a body diode. Okay, most power FETs have a parasitic diode, but it's not a very good one. Okay, so if you notice, they have a second diode, and it's actually in the die. They put it in here, so there's two dies. Okay, so there's the MOSFET die, and then there's the diode die. And the reason they put this is because this is a much better diode. And I believe sometimes these are Schottky diodes. Okay, so this is the difference in that this is a synchronous. It's made specifically for that. And the reason they use a Schottky diode is because the TRR, or the reverse recovery of this diode, is not that good. This one's much better, so that's why they put that in there. Okay, now the other thing that I want to point out here is the electrical characteristics. Okay, and when you're looking at the electrical characteristics, you're actually looking, you want to look at this QG. Let me see if I can expand this. Okay. Okay, total gate charge, and if you notice, it's 200 nanocoulombs. Okay, this is the total. Let me go ahead and zoom back out. Okay, the QG is the total capacitance looking from C to G. Okay, and what it does, it includes CGD plus CGD. This is a Miller cap. And this, depending on the gain, can be huge. Okay. So how do I convert from, remember this is units of coulombs and capacitances in farads. So how do you convert that? Okay, so the way you convert it is CGS, and you do your QG. And then if you notice in here, they give you the voltage where they measured this QG. Okay, so you divide by VGS. Okay, so in this case it's 200 nanocoulombs divided by 12 volts. Okay, so 200 divided by 12. Okay, and this is 16.6 nanofarads. Okay, so now we got that. Okay, so now remember I said no free lunch. Okay, so let's do this. So you have a driver This driver is connected to 12 volts and it's grounded, and I'm using the model, or at least I try to model this driver, this IR1715, this one. This one, if you notice, is F. It's connected to this F here, and then C is connected to this C. Okay. So let's say this is the forward. Okay. Well, that is going to power this MOSFET. This is the forward. Okay. And remember, this one, both the forward and the catch, we're only using 0.5 watts. Okay. So now the capacitance, looking in here, we said it's 16.6 nanofarads. Okay. So this has to charge and discharge pretty fast. And every time you charge, you have a current. And when you discharge, in other words, you sink, you have a current. So basically your current is going to look something like this. It's going to look something like this, something like that. And these are huge currents. We can calculate that a little bit. Okay. So anyway, that's the idea, that to change these from 0 to 12 takes amount of current. Huge currents. Okay, so let's calculate how much power you would dissipate. And this is the power formula for switching. Okay, so since this is switching a capacitive, you can use this formula with quite a bit of confidence. So it's 16.6 nanofarads times 12 volts, and in my case I'm using 150 kilohertz. So let's see how much power we're going to be using. Okay, so we're going to say 16.6 to the negative 9 times 12 squared times 150 kilohertz, and it's 358 milliwatts. Okay, so this is the power loss just running the forward. Okay, 358 milliwatts. Okay, so now you also have the same situation for the catch. So then the total, right? So you just multiply times 2. So you're almost to a watt. Okay, this would be the power to power both the forward and the catch. Okay, so this power you have to add to the switching. Which was, so now you're at 2 watts. Okay, so like I said, you don't really have free lunch. You still end up using a little bit of power, but remember before it was 5.2 for a diode, and now we reduced it to 1.2. Okay, so that's what I want to go ahead and make you aware. Okay, so now these are the challenges. As I mentioned, the driver can be a challenge. In this case, it's a challenge if we have big MOSFETs, which is what we have here. These are huge MOSFETs. These are used for space systems. Okay, and I go to the duration, but take a look here. Basically, when you have a big CGS, that means that your CGS is going to go up, and if your CGS goes up, then you need more drive. You need more current to drive it. So the bigger CGS, the more drive you're going to need, the higher. Okay, and here I showed how to convert it. Okay, and here's an equation. Let me see if I'm going to use this right now or not. Okay. Okay, let's go ahead and use it at this time. I went ahead and used let's see if we can look up IR 1715. I may have to use the UC version. 1715. Okay. Might be the UC. Okay, we're gonna go ahead and use this one, the UC17. Just bear with me. Okay, here are the two drivers, and what you want to do is when you're looking at a driver, basically if you have a big capacitor, in this case the capacitance of the MOSFETs, you want to be sure that you have enough power or current capability. Okay, and okay, we're going to use these equations. Okay, what you want to do is you look for the rise time and the fall time. Rise time and the fall time. And what you want to look is you want to look for this. This is the rise time and fall time. And we're going to go ahead and use 25 as the best case. But you also need the capacitance that they tested at. So in this case, it's 2.2 nanofarads. Okay, so that's where I use this equation. Okay, here is the capacitance that they use, and I believe I took the average from 30 and 20, 25. I took the average. So when you use this equation, RO, what this tells you is this is the output impedance of the driver. Okay. So that's real good to know. In this case, it's close to 6. Let's just run it off to 6. And you can use this value to model. Model your driver. Okay. So now You can also use this equation. This tells you that the driver can only produce 1.2 amps of drive circuit or drive current. What does that do, or what does that mean? Okay, well, it tells me, let me go ahead and do a little bit of calculations here. Okay, let's see how much drive do we need. Okay, so you can use this equation, and we know that CGS is 16.6 nanofarads, and we're going to drive 12 volts. Basically, it's going to go like this. Okay, and typically we want this maybe around 50 nanoseconds. Okay, the faster the better. Okay, but 50 is a good. So we put that under here. So this is what we need. So let's see how much current we would need to drive CGS in 50 nanoseconds. Okay, so let's go ahead and do that. It's 16.6 nano times 12 volts divided by 50 nanoseconds. Okay, so it tells me I need 3.9 amps. Okay, and if you notice, so basically the iDrive ID of the 1715 is less than iDrive that I need. Okay, so I need 3.9 amps, but the chip can only give me 1.2. So what's going to happen? I'm going to have a slow transition. In other words, this, instead of being 50, it might be 100 or more. Is that a problem? Yes, it could be, because if it's slow, you might have cross conduction. In other words, instead of having a dead band, you might have something that looks like this. And then this area, you get cross conduction. Cross conduction. Okay, so let's take a look at that. Okay, the model, it has an output impedance of 6 ohms, and I'm driving it directly from here. So if we take a look, okay, let's take a look. This is the current, and if you notice, this is the current going through the primary, so it's got a huge amount of current here. Okay, these are the switching gates. So let me go ahead and just light up the forward and the catch. Okay. Okay, I went ahead and left this on, but I'll go ahead and leave both on. Okay, so this is the catch. So it's supposed to turn off, but instead of turning off fast, you notice it lingers. Discharge is very slow. And then the secondary, or the primary and the secondary, turns up, and it's got a little kick here. So basically right here we have cross conduction. How do I know? Because I got a lot of current here. See right here? That's a lot of current. Then once the transition goes below 4 volts, right here, then this is on, and which is the forward, and then this is the catch, it's off. And then if you notice, there's another transition here. It's very slow. If you notice, transition is very, very slow. Okay, so that means that my driver doesn't have enough of drive. Okay, so those are the things that you want to look at, and you can tell right here just by looking at that peak. Okay, that's what you want to watch out. So let's go ahead and see if we can fix it. Okay, so one of the remedies that you can do, since this can only supply 1 amp, 1.2, you can put a little driver here. Okay, so let's go ahead and move this connection out to here, and we move this out here. Okay, and change this so just to ensure that it has enough drive. Change it to 5.6. Okay, okay, the simulation should be ending. Okay, let's go ahead and make this a little bit viewable. Okay, now if you notice, the current sense looks well behaved. Okay, remember we had up to 3 amps. Now you just have a little bit of a leading edge. So let's take a look at this here. Now remember how the catch, let me go ahead and take this off. I'll take that off. That one. So we can see now the gap. Okay, so now if you notice, this comes down a little bit faster. Okay, well, I would like for it to come down a little bit faster. I could probably put up a speed up cap and make it discharge faster, but that looks pretty good. And then it goes up, and then you have this white deadband. Okay, but the point is we don't have any cross conduction, so that looks real good. Okay, so that's the point, the main point that I want to show, that yes, you can use a MOSFET and you will save power, but you also want to be sure that the power that you're wasting or that you're driving from your driver is still low enough. You don't want it where it becomes the dominant part of your system. So anyway, in a nutshell, that's what synchronous power is, or rectification. If you have any questions, you can email me at rbola35618@aol.com. Any comments, you can also mail them. If you found this video informative, please subscribe, thumbs up, and share the video. Thank you for listening. Thank you.